these new cores. Declan, thank you. Okay, great. Okay, new cores. So what I've done is, in the last few minutes, literally, I've emailed you just a quick, rough getting started guide. I also built a module in the learning management system on Canvas on the new hardware and how to put everything together with all of the links. But I thought maybe that wasn't enough, so I backed it up with a PDF that I've now emailed to everybody. So what it is that first of all, it will recognize all of the other sensors that you have. There's just one exception that you need to be aware of, and that is that the soil moisture sensor and the accelerometer, I don't know, Bjarke, what they have the same address or they use the same pins or something, but it doesn't like it when they both put it at the same time.
Yeah, so unfortunately, the accelerometer have an interrupt pin, which I think I'm gonna take away in the future. And that interrupt pin is shared by the soil moisture sensor pin. So they can't both be in the same circuit at the same time. And not that I can ever imagine you want to measure soil moisture sensor and acceleration at the same time, but hey, you know, when Jim and his team start testing soil moisture on the moon, you might want to. So yeah, so on the back of the accelerometer, you can see there's a little, well, I don't think you can see it actually because I didn't make it like that. But in the future, what I'm gonna do is I'm gonna make the interrupt optional, which means that you have to then solder on it if you want it to work. And then they can work at the same time. So yeah, they have a problem at being in the same circuit at the same time, and therefore the new starter kits or STEM kit software does not include the soil moisture sensor, but there is a separate app that you can install that do the soil moisture sensor alone. But I think Judy will come back to that.
Absolutely. Thanks, Bjarke. Please explain. Sorry, let me rephrase that.
Yeah.
What's your story? No, please share with us why there is an interrupt pin on the accelerometer.
Okay, so lot of the sensors have interrupt options, and the idea is that the way sensor works today is that you will ask it, if you can imagine your classroom, to take an analogy that is suitable in this audience here. You will ask the students, please answer this question, please. So none of the students will say anything before they are drift. I mean, I'm talking about technology, not the real world, of course. But the idea is the student is, the sensor is only answering when they're being addressed. And then interrupt is that you actually say, no, the student have to interrupt me in a certain situation. So on an accelerometer, for example, you could say, listen, if the acceleration changes from, let's say, 1G to something more, then you want it to send an impulse. You want to be interrupted. Now, the way that works is that you can then program your computer core to, for example, sleep, and then be working up on that instance, which will save battery power because the computer core costs power when it runs. And you can therefore also activate something. You could also just have it awake, but listen to that specific pin and say, if something happened here, then I want to do something. So an interrupt is like that. And some of the other sensors could also have interrupt. We just not chosen to implement it because and requires special coding that not necessarily is suitable. An interrupt could be suitable because, let's say, for example, you want to measure when an acceleration happen or something happen, that maybe happen in like a millisecond. Like, for example, if on a high altitude balloon flight, the balloon pop, and it will be like a short interruption, and it might go back to a normal lower thing. And if you didn't have the interruption, then you might not have asked the accelerometer in the right time if anything happens. Temperature doesn't really matter because you will ask the temperature, let's say, every 5 seconds. And if it changes suddenly to like a boiling point or whatever, something where you wanted to react, you might be fine that it tells you at that point. So just a long story about why we have interrupts.
Okay,
yeah.
Great.
Declan had his hand up.
Yeah, sorry. I just wanted to mention something which might be a bit interesting.
By the way, the way that Declan put his hand up, that's how the interrupt works. It's not actually interrupting your code. It just like puts its hand up, and the computer core, me, are then saying, okay, let me hear, what is your story? Declan, what's your story?
I wanted to mention that I was playing around with the microprocessor recently by a company called Nordic, who create the Nordic chips. And they do an interrupt system, but they sort of they've got a system baked into, or a chip baked into their embedded suite or their circuit boards, where instead of having it be component side interrupts, it actually runs on an extremely low power. So it's used a lot for wearables and IoT, runs on an extremely low power. And then it has a chip. The only purpose of that chip is to determine very minuscule or simple changes in, say, a button push or a major change in accelerometer, to then call back to the CPU to wake it up, like you said. But instead of being component side, where it depends on the manufacturer and you have to add another interrupt wire, what Nordic do is they actually just have a chip on board which does that function for them.
By the way, NRF chips, so this is probably like NRF 52 or something like that, doesn't have Wi-Fi, it only have Bluetooth. So therefore, it is by nature very low power. The ESP32, because it have Wi-Fi, is not by nature low power. But just if you really want to go into details, our computer chip, the ESP32, have 2 cores, but it also have a low power core that you can program. So there is an option for running low power, but now I think we are way beyond what we need for this.
Great. Bjarke, Declan, thank you very much. So what I'd like to do is I'd just like to share my screen with you so that I can explain what I meant. Now I've got to find the one that I want to share with you. Interesting. Sorry. Yeah. Okay, there we go. Right. So I think you can see this is the GitHub site that you're going to be directed to from the documentation that I've done. So it's domino4com.github. Yes.
It's had to have been changed. It is now apps at MaxIQ.
Okay, Bjarke, can you put that in the chat,
yeah.
please? Can you just put the link in the chat for me? Thanks, because I was going to say that is we actually have a much more intuitive link that actually goes to this page. But you can see here that what we have is we've got there's a number of different code modules here. So we have the normal STEM starter kit. And so this one recognizes all of the sensors except for the soil moisture sensor. So if you want to use the soil moisture sensor, there is different code that you can just download for that. But you're not going to be worried about that for our ISS project. And then when you get to the point where you want to build a tiny GS ground station, there is the LoRa-based tiny GS ground station code there as well. So Declan, you have all of your other components. You can still use the radio module. For anybody on the call who's built the previous tiny GS ground station, you can use the same radio module, and then you can just use this core, this code here with your new core. And Alex, for you as well, I'm going to make sure that Alex, that I send you the LoRa radio module that we have, so that you can also build a tiny GS ground station, because I know that that's right up your alley. And then, yeah, there's some MicroPython here, I2C scanner, which I find very, very useful. When we test all of our components, I use the I2C scanner. And then this quest, this is not a typo, it is meant to be a double ST. This is a trial that we're running at the moment with Virginia Space with the sound pressure sensor. So once we've completed that trial, etc., then we're going to be rolling it out to everybody. So that's why we say if you want to use the soil moisture sensor, it's different code. So that is the thing with this core. Then you also have in your pack is that you have a small number of these USB-C male-to-male connectors, because when you program it, or when you drag and drop your code, you need to connect via USB-C. It's not going to work. You're not going to be able to code or program using this USB-A as you did on the previous core. Okay. So once you have, now the thing is that all of you, we needed to ship these new cores to you before the code was finished and tested. So we have the bootloader on it, but you're going to need to put the code on yourselves from that site and the link that Bjarke has given us. Okay. Okay, I can see. Let me just see what's in the chat. Okay, yeah, Richard. Can we get to that in a few minutes about any new components, etc.? I just want to get through the basics of this. So yeah, so in order to program with your new code, you need to use this you need to use a USB-C connector. I mean, I have a USB-C for my laptop, etc., and for everything else. But there's a number of people who don't have readily available USB-C male connector. So that's why we shipped some of these with this new shipment. And then also what we've done is we've also included some of these SD card interfaces for you, so that you can start working on your code to save your data onto the SD card, because that's really how it's going to be operating when you're on ISS. So this then works with this 20-pin connector. So that's going to be this core that you have now has all of the components on it that you're going to have on your NanoRacks core, which is the core we're going to use for the ISS. So it slots in here nice and neatly. So now you can start working on getting the data from all of your sensors to the SD card. Bjarke, I'd like you to come in here in terms of you were saying the other day something about how you've done some code that does that.
Will you allow me to share? I put in a link in the description here, dominofort.com/CWA. So if you have to program against the new core, or actually the old core, doesn't really matter. You go to that website. So let me just share my screen here, which is this one here. Okay, so you should be able to see now a GitHub page. So if you go to domino4.com CWA, capital letter CWA, you should get to this page here. That's it just redirects to GitHub domino4.com CWA. Underneath here, you will be able to. This page has been there for a very long time, so it's not like it's new. Other than it will talk about version 1 and version 2. So on the version 1, which is the old core, with the touch buttons, that of course have these touch buttons, and this is how it's connected. The new core from version 2 has these 2 buttons. The one is a program button that you can actually program using IO0, and then they have a reset button. And those 2 buttons are being used not only in your own code if you want to use it, but it's also being used with the bootloader and how you program it. The old one had 5 different LEDs, actually 3 different LEDs. Some of them had multiple colors. The new one have 2 LEDs. The one is red, and the other one is a NeoPixel, which can be any color you want. If you go in, if you program it in that Arduino, there's something called RGB color under ESP32, and there's a single line you can write where you just say what color you want it. Then of course you have the different pins you're using. So I2C, the way you communicate to the different connectors, the one that Declan have fallen for, and he's very helpful to tell everybody else about on Discord when they forget it, is that we have these pins for the old core, and the new core is like that. The good news is with regards to these pins is that we do also have a new extended core coming out. Actually, it's in production as we speak. That's the reason why you haven't received it. But that core have exactly the same pin as the CWA version 2. So the SDA and all the other pins are the same LED pins, the same everything. So when you program something to this new core you're getting and you want to transfer it over to the extended core, all the pins work the same. There's one little difference, which I will make clear just now. So the serial port, not that you necessarily use it, have these pins. And then there's this I/O pin, the one we talked about with the interrupt pin for the accelerometer, or the pin that's being used with soil moisture sensor. That was an old one, pin 2, and the new one is pin 1. And then there is a pin that's called double tap that you can't really use. It's kind of called a 1-bit memory. It's something that's put in order for the circuit to be able to work with uploading code that Judy might show you just now. It has an expansion port which the old one didn't have. And if you want to address the SD card, you have 3 different ways you can connect to the SD card. So there's the SPI where you have Mesomosi, and then you have a chip select with your typical X1 here. And then you can use a normal SD card SPI to contact your, to read and write to your SD card. But you also have another way that's called MMC. So again, you install ESP32, there's like a lot of examples. There's something called SDMMC. And they have like what they call a 1-bit and a 4-bit way of getting data. And that's the reason why we have, you can see the 4-bit is that 0, and that's 1, 2, and 3. And when you write to the SD card using MMC 4-bit, it's vastly faster than actually even writing to the internal memory. It's incredible fast. And that's going to be interesting when we do rocket flights and things like that, model rocket flights, where we have a lot of data we want to gather in like few seconds. This MNC way of writing. So both the extended core and this core you have in your hand have this expansion port, and it's the same pins. But the new extended core also have a separate SD card that doesn't have this fast way of recording, which is fine for the International Space Station. So you can have two SD cards if you want on the ISS. But the one that's built into the SD card will have the same MISO, MOSI, and SDK, but will have one other pin for chip select. So you can choose which card you write to. So the one with the expansion port, both the one you have there and the one in the extended core, can do this 4-bit MMC. The built-in on the CW, the extended core, can only do normal SD card read and write like you used to in an old one. So this is the sheet you want to look at when you start programming. So remember, when you start using any of the sensors and things like that, then you have to start with a wire begin and then say 1718 to 17,18 to kind of like tell that this is the pin to using to read the I2C with. Judy?
Great, Bjarke, thank you. If you wouldn't mind stop sharing, that's perfect. Thanks. So once you have everything, once you have your code on your core, then you can use this USB-A power module. It works for power. It just doesn't work for programming. So you can go back to just having using this from a convenience perspective, this USB-A. Once you have programmed your core. There is another thing as well where it's a lot more convenient. What you'll see is that once you drag and drop the code to the core, especially the starter kit code, you'll see it will start scrolling. And then in order to connect it to the Wi-Fi, all you need to do is just on your computer or on your phone, just browse to that address. You don't actually have to then put a password in. Once you connected and you configured the other settings and given it a name and given it your SSID and password, etc., then it will connect automatically. So that's a lot easier and than it used to be with the previous version of the core. Yeah, so I think at this point, the training wheels have come off. Those STEM kits that we initially sent to you, that's great. But yeah, now that we have our new processor and our SD card interface, etc., the training wheels have been taken off so that we can, because we're going to pick up the pace getting ready for the ISS. So at this point, do I have any questions? Because I'm going to start going through what the deadlines are. But do we have any questions at this point? Declan.
So from my side, I didn't have any trouble with putting in and programming with the precompiled codes. But I've been playing around on my own to try, run my own code on there. And I've used a UF2 converter, changed the family name to the one which is on the board and in the README file. I've used the tiny UF2, but for some reason, I can't get my UF2 files to get accepted. They get loaded onto the device, but it doesn't actually do anything. Is there some part of the process I'm missing for compiling my own UF2 files or custom code to load onto the device?
Bjarke?
Yes, I don't know. I don't know what you're doing, man. But I can tell you a thing here. I have done the software that's with the UF2 here, and I have put it together using Visual Studio Code and Platform IO. And the reason I have done that is because I have incorporated in my setup that it automatically do a UF2 that can then be loaded off. Okay, so I'm going to release that code, the open code, so you can actually learn from that code and see how that works. So allow me just to show what I have done. But actually, before I do that, Declan, Judy, are you going to show how you put the code on the new core?
I don't need to. If you want to show everybody, I'm very happy that you do that.
No, that's fine. So let me just. So what I want to show as the difference is, and I'm going to share my screen again here, which must be Chrome. Share. So what? If you see on my screen here, if I go to apps, MaxIQ.space, I get this screen here that Judy was talking about before. There's two sections to it. There's this section here where it says how to put the bootloader on. And Judy have already put the bootloader on the core you have there. And then there's this section down here where you can put a ready-made UF2 file on it. If you program your core in anything, so you plug it in and you go into Arduino and you say, this is my new code, I want to program it and that kind of stuff. Then you overwrite the bootloader. So then you have to put a bootloader on again, okay? Now, putting the bootloader on is a very straightforward and simple process. And I'm gonna just quickly do it here with a core, see if you can find one. So, so let me just get my camera straight here. So I have now plugged in a core here, you put in front of my face. And the thing is that I just have to be unlocked and locked. That is one of my work in progress. But let's see. So if I then click on install up here, you can see it comes up with a window, hopefully, where it says...
it doesn't. It's not coming through on the Zoom. No. Oh, wait.
And it's,
no, something's coming up now.
Okay, but that's because I said cancel. So let me just reshare, and then I just reshare my whole screen here. So let me just stop share, and then share again. And then I'm sharing desktop here. Now you should see my whole screen here, okay? So so this one here, I can put it into programming mode. So there's two modes that you can do here. That one is native to the CPU, how it comes from the factory, and that is, as it says up here, if connection is troublesome. This part here, if the connection is troublesome, then you click the play button, then you press the reset button and click the reset button, I should say here, and release the button. So the way I do it is I use one finger, I click first on the top, then I roll over and click on the bottom one, and then I release it, and then you can see the red light comes on. Now it's in the native bootloader mode, the programming mode as it's called, okay? And when I do that, then I can click install. Can you see the window now, Judy?
Yes.
Yeah, okay.
Yes.
So up here, you can see I have a port called Bluetooth, that doesn't matter. And then I have this USB JTAG CL unit here. And if I say connect to that, it tries to connect to it. And then I can say install the Domino 4 UF2 bootloader. I can say erase device, I say next, and I say install. And then it installs the bootloader to this core here. So if you have, so this stuff that I did now, Judy had done that already with the core, so her team. And if you program it over this thing here, then you have to do that again if you want to install UF2 stuff on it, okay? So this takes up, of course, a little bit of memory that makes it much easier. And as long as you, if you just keep installing different bootloaders on it, then different UF2 files on it, it will still be there. But if you program something from scratch, you will override it. Okay, so now I've done that, and I can actually go into a console here, and I can say reset device, and then I get, like, you see it's in waiting and boot for download because the red light is on. So if I click on the reset button, the bottom one here, the red light goes off. This one actually says that had lost the connection to the device because I booted it. Now you can see the red light here is fading in and out, okay? On yours, it might also actually have the other lights coming on, the green light coming on underneath. So there will be the mine here doesn't have it, but yours will have a NeoPixel where the green light comes on, okay? So now we're in this situation where you can actually just program a UF2, and this is the part that you actually have to do yourself because yours will come like that. And you can see that that red light is kind of like pulsing, as it's called, okay? So you can see up here, it says click on reset after successful install. I see that drive will appear on your computer and the green light will continuously illuminate here, okay? So if I look here, you can see I have a CWA drive on my computer now. I assume that came up, okay? So I have the CWA drive, and what you do now is that you take a UF2 file and you just drop it into that. So I'm going to do that by going here and say, well, let me, for example, and I'm just taking a random example here. I'm taking the I2 scanner here, and then I say, okay, now I have downloaded that file, just download it to my download folder. So I can kind of like open my download folder here. And then I have this I2C scanner. I drag it to this file here. That's how I program it. And this thing here blinks, and then it's programmed. And then this thing here says can't be completed because it disappeared. Yeah, it disappeared because you now have something installed, okay? And if I quickly plow in a display here and reset it so I can have it running, you can see here that it now plays something on a green screen here, on a screen, sorry, it's not very focused, but that's actually, I'm just playing around with I2C here. I have it writing the other way around so I can have much more on the screen. So if I put another sensor on, that's how a I2C scanner work. And now I'm going to put something interesting on that you haven't seen before, a new sensor that is coming out also at a certain point. This is the time of flight sensor. It measures the distance. So it uses, and you can see now there's 3 lines here that shows the I2C address here. So you can use this thing here also if you kind of like think that Judy sent me a sensor doesn't work. In reality, you know, it's your student that can't program. Then you go in here and prove to them that they can't program and Judy didn't send something rubbish, okay? So this is how it works, okay? So now what I can do is I can, I want to get into UF2 again. Now, when I did it first time, it automatically goes into UF2 bootloader because there was nothing on it. But if I want to stop this and get it back to UF2, then it says here, connect you to a USB-C port, download the file, and then double click on reset button. You see there's a reset button to put it into UF2. So if I take the screen out, and then I double click on the reset button here, then you can see, sorry. There we go. then you can see it does this pulsing. Okay. Now that pulsing is different from when I put it into program mode, which what I did above, where it's just have a steady red light on it. Okay, this is the program mode for, and that program mode is also good if you feel that you bricked your thing, your core, you can't program, it's like locked up or something like that. You put it into program mode, it will always work for you. Okay. So now what I'm doing here is I'm just double click on the reset button. Sorry. Let me just, come on. There we go. I have to double click a little bit slower. so now it's in that mode here. And if I then say, for example, the starter kit, which of course is what you really should install on this thing here, I go here and I have the starter, I drag and drop it into CWA. It's programming. And then, of course, I'm going to put in the display again, like that. And if I put in, anyhow, let me just reset, because you will see it's like that. So if I just reset it, which is just do because, and you can see here, some other code pitches up. Okay. So that's how this is done. So I'm gonna just disconnect that. So you will have you will appear as a drive. Now, if you go into, okay, so now I just illustrated for you the fundamental in what this UF2 is. So UF2 is a wrapper that takes an existing compiled file you have and wrap it. So when you do this drag and drop around, different entity can understand this UF2. It's something developed by Microsoft, and it's what the microbit does when you program, for example, microbit. It's actually you're making a UF2, and this is just the same technology that's been used here on this ESP. And therefore, you can also, just because I think you might doubt this thing here, but you can actually, if I take this thing here, I double click on this thing here, I can actually go in here on this screen, and I can say to let's say the I2C scanner, right click, and I can say save link as, and I can save it straight to the CWA like this. So I don't even have to download it on my own computer. I can just take it straight into this thing here, and then when it's and then you can see it started its new code here. So you can do it that way also. Now, here comes the whole trick if you want to do any of this thing here yourself. But first of all, if you just want to program it, you don't have to do UF2. You can just program it. So if you open up Arduino, one of the things you have to do to program it is that you have to go in under, and first of all, I'm not going to necessarily teach Arduino or anything like that. I kind of like assume you're going to watch the 600 YouTube video and learn everything about it. But if you are going to program this thing here, and you may be familiar with programming Arduino for Arduino Uno or anything like that, what you do is you go into board files. So the way you can do it here is that there's some side buttons here. There's one here called board. And what you do is you go up here and say ESP32. And then there's a board file here, and you can install that. I seem to have installed the one from that's called Arduino ESP32, and installed this one here, and I installed the latest one. So that worked fine. There's also one by by Expressive. For some reason, I've chosen that one up there. There's sometimes there's something where somebody on like some forum has said, no, you should install that. So this is the one I installed. Once you've done that, you will be able to go up here under examples, and you will see here the examples, especially for the ESP32S3. Sorry, you have to tell first that you want to run the ESP32S3. So here when you install the board manager, you can see up here at the top, there is a different ESP32. The one you have in a new core is called ESP32S3. Judy, if you will put that in the chat. ESP32S3. The old core, the old one we had on the old system, was just called ESP32. So this is the new S3. And it has like a lot of different things that's nice. First of all, it's another architecture inside. It's a RISC computer. RISC stands for Reduced Instruction Set Code. But it's also double the size in memory. So it's 8 megabytes instead of 4 megabytes. And it has this native USB connectivity. And that means many great things. One is that, let me just show here. If you go to examples, and you've chosen that you have ESP32S3, you have all these different examples here, all the way down to, this is other libraries I installed, but all these examples. So here's, for example, if you want to do SD card read and write, and here for MMC. Remember to set the pins. In all cases, you have to set the pins as I illustrated earlier. So there's a code for Wi-Fi, there's web server, and there's a lot of different USB. You can have it as a USB memory stick. That's called USB MSC. So if I run this code here, and I'm not trying to tell you how it works, you maybe go into the code and you can figure out that, for example, there's a README file, and this is the text inside the README file. And you can go in here and you can give it your name instead of calling ESP32 and USB-C and C and things like that. And what then happens is that once you program it, it will work as a memory stick. So you can actually plug it in to your computer as a memory stick using, for example, the little connector that Judy is showing you. So this is one of the things. You can also program it to operate as on the USB as a mouse, for example, and it can work as a keyboard. So instead of you having a keyboard, you can plug into a computer and get it to send an instruction so it actually looks from another computer as you type the program and type the sentence. So there's a lot of different programs. I'm of course not going through all of them, but there's a lot of tutorials and examples out there on the internet of different users that are taking one at a time these different examples and run them. But what you need to run them is just your core here. None of the other stuff is needed for running these different examples here, unless it says so. So that's the other thing that's very, very important programming-wise. And this is something that it's not normal for embedded programming. So in the normal programming world, you can typically with a programming language, you can run in debug mode. And what that means is that you're stepping through the code, one code line at a time. So you're stepping through, and every time you go through a step, you can then go with your mouse and highlight a variable and see what's inside that variable. What we normally do in embedded programming is that we do a lot of serial print line. So we print all the variables everywhere when we try to figure out what it is. But up here in the corner, you can see there's like a start debugging. So let me just close this thing. There's a start debugging here. So if you run this thing here with debugging, you can then debug inline in this thing here. And that's because of the USB 2. There is built into the USB 2 a JTAG debugger. So the Arduino support that already. So if you have some code and you don't understand why is it doing that, you can go down and you can see, hey, this if statement made it jump or call this routine. I didn't expect that to happen. So instead of going into the code and put in, a debug statement like cl.println everywhere, you simply just run debug to find this thing here. So that's just a facility for over the USB 2 that makes it much easier. Of course, you have to learn it first, but it makes it much easier to run through code that you have on this thing here. And it's a very important coding skills in general to be able to debug using these inline debuggers. So that's the stuff. And the last thing I just want to show is that this was Arduino. If I run Visual Studio Code, and I'm busy looking at this library here, ILB, that doesn't work. I haven't actually had time to finish that. So if I close this workspace and open this one here, it's going to have a new name. But this is actually the STEM software. And the way that works, which is different from Arduino, is that you have a file here that's called platform.ini, platform.io.ini, where you go in and you define all the libraries you're working with. So I have one for each of the chips, and then I have a number of general libraries I'm using. I also have created a lot of flags that I can set up outside. So for example, the MQTT password I have in an external thing, but like all the different hard-coded stuff I have put in parameters outside. And then up here, I can say I programmed that for CWAV2. So I have that down here. But if I wanted to put in, like I could program something else, you can see all the pin configurations I put in here. So they're not inside the program. So if I have another core, I can actually just copy that section and say, now I want to program to that core. So everything is kind of like set up out here. So you can see the entire environment here. What I also have here is that I've told that I have an extra script. I have this uf2.python. It's a Python script I want to run afterwards. You can see it says post here. So over here, let me just close some of these folders. Over here, I have a script that's called uf2. So it will run that once it finishes compiling. And in this thing here, it will first figure out if it will run Linux on Windows and on OS2, for some reason called Darwin. So, and then it will run this uf2 conf file a little bit different because the operating system is different, the filing system is slightly different. So we'll do that. So this is the wrapper that I'm using, Declan. When I release this code here, you will get this entire thing here, okay? The other thing I also just want to show is that I've done these uniform libraries. So for example, in my main, I'm main.8 here, I say I want to include ilc.8 and then instantiate. I have iwa.8 and I instantiate. So this is the one place where I refer to my sensors. And in the main code, I simply just, I have the same begin because they all work the same way. And then down in a loop, I'm actually just, if it's online, I pass a JSON that gets filled up for each of the sensors. So this is all the codes to all the different sensors. There's nothing that's special. And the last part is on a display. I say if it's online, I draw different frames. So if you haven't plugged in a sensor, it doesn't actually draw that frame. So the frame, when you will see in the code, it jumps from frame to frame. And of course, the frames is then up here. So here's one for ambient light. Here's one for magnitude on accelerometer. Here's one for some GPS. Here's a CO2 and so on. So that's the code. I will release that. I just need like a little bit of rename and things like that. And then you will be able to see how I program and what I am doing in this space here. Judy, I think this is enough from my side right now, because otherwise I'm pretty sure I overload everybody. But hey, I can still talk for 2 weeks if you want me to.
No, please don't.
sorry.
Declan is interrupting. Go ahead, Declan.
Sorry. I just wanted to quickly ask, could you please show again your settings on tools, your upload speed board, and I know the board is the ESP32S3 dev module, but can I see your upload speed and other settings?
Yeah.
Because
so
I have been having some trouble uploading directly.
Okay. So if you want to do it directly, so I'm just gonna plug it in here. Okay. So I plugged it in, and then I'm just gonna take a simple sketch here, so you can just see how it is. Okay. So if I go into examples and take the symbols that exist, blink. Okay. So here's blink. Now,
your screen isn't showing.
Oh, that's good. Let's show my screen. Here we go. Okay. So first of all, let me just go to domino4 .com/CWA here. Okay. Okay. So down here it says the LED. The red LED is IO40 here. Okay. So let's go to Arduino here. I have what I did was that I went into File, Examples, Basic, and Blink. That is the simplest thing you can start with if you want to program this thing here. That comes up like that. It expects a define that's called built-in. So let's define that. So we say define built-in, and the red pin was 40. So now I have put that in. In order to program this thing here, when it's over USB, the speed doesn't matter. It doesn't matter what speed you set it to. It will always just do full speed because USB is not 0. So this is upload speed for 0. So the only thing I will change here is I want to say this thing here that's called CDC on boot. I will make that enabled if I use the USB connection, okay? Because if I use the USB connection and I do a serial print line, I only see it if you have enabled this thing here, okay? The other thing you should change is the size of your flash, because it's 8 megabyte and not 4 megabyte. It doesn't really matter if your program is not very big and you put 4 megabyte, you just don't use the whole thing. But if you think you're about to run out, I mean, I have to say, my other program is the big one I made is not 4 megabyte yet. It's still room for running 2 programs on the same machine. Anyhow, so that one I changed, and then I changed the flash size, and the rest I don't. I go in and I point to the USB here. You can see it says ESP32 family device. So that's the direct connection over the USB here. And then, of course, the ESP32S3. So this one, you have to connect to your USB port. These two are the normal ones. Otherwise, it's a USB-C CDC unenabled if you use serial print, which this example doesn't do. And then 8 megabytes, just might as well remember it. When you have the extended core, not this one here, but the extended core, you will have PS RAM also. So on extended core, there's PS RAM. So that's another 16, and that's, I can't remember which RAM it is. I'm going to document it when the core comes out, but there's like 2 different ones. I think it's a QSPI PS RAM, but you will say you enable that, which allows you to have a lot more RAM. It's actually only important for certain concepts. I use it when I do AI on the chip, and I use it when I do the camera because it can store a whole frame buffer, which you want to store like 25 times a second. So therefore, you want to have a lot of RAM. So that's what the PS RAM is used for. The rest, I don't really.
Sorry. When you're programming, just one more thing. I assume you're doing it when it is accepting the like, I know you set up the chip so that it's able to accept the UF2 files by pressing the reset button 3 times so that it appears as a drive.
2.
Are you uploading? Oh, sorry, yeah, 2. When you're uploading, are you doing that in that setting or not in that setting?
No. So what you can try to do, so the way it works is that the USB should be able to automatically put into programming mode. But if that doesn't happen, you can help it into the programming mode, okay? So the way you put into programming mode is the play, reset, play, so it comes in with a steady red light, okay? So the top one, play, and then reset, and then play. Well, play, hold it down. So let me just do that right. You press the play and hold it down, and then you click on the reset, let go of the reset, and then you let go of the play button. That way, it goes into this thing having this red light, which is then a programming mode. Okay. Now, in programming mode, then you will never have a problem with anything uploading. But if it's not programming mode, maybe it's like something where it's using the USB drive, and therefore you don't choose the right drive and all that kind of stuff. So if it doesn't work just right out of the thing, you can just put it into programming mode here, like I just did, and then you can just program it. So if I click on upload here, so you should be able to see that on the screen. You can see here, it set some of those parameters here. So CDC is on, and the flash size is 8, and then it compiles, and it shouldn't take too long time when it's such a little program, but hey. And if I put in a zero, yeah.
Sorry, Bjarke, I need to interrupt you soon because we're 1 minute over time. And okay. I need to finish off, but that's fine.
Let me just, this thing here, it's uploading, so it's ready in, give me 5 seconds, then you can see here. And then, and now you can see the red light is on because it's still in programming mode. If you put it there, it stays there. So now I just click the reset, and now it blinks like that program that you're looking at the screen says it had to blink once a second. So now it's running the program. But if you put it into programming mode, the red stays solid, and now it's a programming mode, and it doesn't run anything. Declan, did that answer? Judy?
Okay, great. Thank you. So, yeah, I've asked anybody if they have any questions, and I haven't had anything there in the chat. So before we conclude today, I'm bringing up, this is our shared Google Sheets with the schedule in tab 3 with the schedule. So this is actually technically workshop 1. And so that's over, this is the first iteration, and then we're repeating it again later in the day tomorrow, just to understand all of the X chips that we have, etc. Our next workshop, we are expecting here, this is the first week of December, and I know exactly what Richard Naggs is going to say. He's going to say, yes, but we're actually launching a payload on a rocket. We'll deal with that. Okay, we'll make sure that we can schedule things in and around that. And then if you do want your payload to be tested on a high altitude balloon launch, you need to be ready then to ship that payload mid-December 2024. So this is it's not a must-have. It's a nice to have if you want to make sure that you're under a number of different circumstances, that your data is writing to the SD card, etc. So if you want to do that, you would need to be ready to ship that to us mid-December, because we will be conducting that launch sometime late December, maybe through January. So workshop 4 will be January 7th, repeated on January 8th, And this is where we discuss your final payloads that's going to go to International Space Station. Because what we have is we do have a deadline. And that deadline is you need to tell us at the end of January if you believe that you are going to be ready mid-March with your payload for the International Space Station. If you feel you're not going to be ready, that's okay. You can delay to the follow-up launch. But yeah, you need to have a very, very good idea end of January if you're going to be ready 6 weeks after that, by 15th of March, Ides of March, to be able to ship to us. Okay, so with that, let me see what's in the chat here. Yes, Bianca.
I just want to answer Richard's question from the beginning. Can I do that?
Yes, let me just see if I've got any other questions here. Okay, Richard is asking in terms of the high altitude balloon project, where is that going to be done? We don't know yet. It's either going to be in the US or it's going to be in South Africa, so we don't know yet. We will let you know closer to the time. And then the ISS payloads are not going to be shipped to Cape Town. They are probably going to be shipped to Princeton in New Jersey. Okay. And then Ahmet is asking, for those in the US, any address where we can ship for the high altitude balloon. Ahmet, you will be notified of that. You're actually going to be, over the next few weeks, you're going to be receiving packaging. And what we always do is that we will send you a shipping label that you simply attach, so that you don't have to worry about, is it going to the right place, all of that kind of stuff. So don't worry about that. We're going to sort all of that out. Yes, Bianca, if you want to go back to that question. By the way, I'm so sorry, everybody. We are running over. So I think if some of you do need to leave, that is absolutely fine. Are there any other questions before we go back and start answering other questions not on the agenda? Is that all okay? Okay, Bianca, please, if you don't mind, not too much longer, because Jim and I need to meet about next week. But please go ahead.
So Richard and the rest of you guys, the high altitude balloon launch or other places where it might be suitable, but specifically because of the high altitude balloons, we are going to come up with a BME 688 sensor, which is the one that Jim Gorman and his student used in their own setup here at the last flight. We also going to come out with a accelerometer that IMU actually, because it's also a gyroscope and a magnometer, which is called I can't remember what it's called, DS91. I can't remember what it's called right now, but we're coming out with one of those. And then we're going to come out with a radiation sensor, a gamma radiation sensor that we are building together with the University of Cape Town. They have a radiation department, and they actually have built a radiation sensor. And this is the big one, but you can see how small it is. The one we are building with the department is actually is going to fit on an X chip. It might have a little column on it for having radiation bombarding it from a number of different sides. So that's coming out. It's a quite expensive sensor. So if one wanna use that, then the sensor itself is very expensive. Never mind when I want money for putting on a X chip, of course. And then the last thing we also gonna try to figure out with ISS is allowing to use camera on the on our extended board. So 3 new sensors plus the camera that should give you a lot more fun in the flights to come. The camera is not going to be at all useful, and there's no camera mount for it for the ISS, simply because we're in a black box and we have to shrink down the extended core, so there's no room for a camera port on it. There's everything else, but not the camera port. And of course, some of the stuff on the ISS, when one considers it's inside a metal box, give limited. But since it's not hermetically sealed, you should still be able to pick up some atmosphere from inside the ISS. Judy, I just have one request, and that is that when we end here, if I can ask Don, Richard, and Declan just to stay around for like 1 minute, and then you can continue with Jim if that's all right.
Okay, so Bjarke, what I can do is that I can make you the host, but then I don't know how Jim and I are going to continue.
But I mean, literally just a minute. So Jim stays in, and then the rest of us leave.
Okay, cool. Great. Any other questions? Everyone good? Great. Yes, Alex.
We met the Princeton team at the Small Satellite Education Conference in Canaveral last weekend.
Oh, fantastic.
So that was a good connection moment for our group.
Oh, excellent. Good. How was that conference?
It was good. This project will be better represented at it next time, because we will have results and everything else. And if somebody else wants to make it over here, we're set on presenting at that conference next year, because to be fair, it's a very low barrier to entry, and some of the presentations were basically just information sharing versus actual research or projects. So we can, and it's only a 15-minute, you only get 15 minutes a slot. So we can do a tremendous amount of work. Our team went deep dive on the Princeton guys and had a whole separate conversation afterwards, which was totally awesome. But
great.
Yeah.
Perfect. Excellent. Thanks, Alex.
All right. I will then check out so everybody else can start their side conversations.
Okay. Have a wonderful day, Alex. It's only just starting now. Okay, yep. Thanks, everyone. Cheers. See you soon.
All right, bye.
Thank you very much. Okay.
Thank you so much. Amit, fly safe. It's going to be fantastic.
Thank you.
Great. Thanks. Cheers.